Okay, I think we're going to go ahead and get started. Welcome to the last Nano at Tech seminar for 2021. Glad you could make it. Just as a reminder, we will be starting up again in 2022. Our first seminar will be on January 11th. Again, that's a Tuesday in January, 12 o'clock noon Eastern Time. And the speaker will be Professor Alan Doolittle from Electrical and Computer Engineering. So it's a real pleasure to welcome today's speaker, Professor Gleb Yushin from the School of Material Science and Engineering here at Georgia Tech. Gleb got his bachelor's degree at the Polytechnic Institute of St. Petersburg in Russia before coming to North Carolina State University, where he got his PhD in material science. He joined Georgia Tech in 2007, where he is currently professor and Mifflin Hood Chair in Material Science and Engineering, and you can see his credentials here, as well as co-founder and chief technology officer of Sila Nanotechnology, which I just learned how to pronounce yesterday, as well as editor-in-chief of Materials Today. He's won a number of awards, including most recently the Georgia Tech Outstanding Achievement in Research Innovation Award in 2019, and is one of the most highly cited international scientific authors. And with that, I will turn it over to Gleb.
You will do. Do you hear me well? David, thank you so much for the nice introduction. I'm delighted to be here and share my thoughts on the importance of next generation materials for all the future lithium-ion batteries. Let me mute my phone if we have it. And so if you think about transition to renewable energy economy, and the massive amount of lithium-ion batteries that would require for this, there are many additional requirements that you'll have to realize and that are not met in the current lithium-ion batteries. First of all, the minerals that go into lithium-ion batteries have to be abundant. The materials have to be of low cost. The battery themselves, they have to provide fast charging and high energy density. And energy density is important for multiple considerations. First of all, you have to have a longer driving range, even for small vehicles. But in addition to that, if you go to higher energy density cells, this cell pack becomes cheaper, less expensive, because you simply need to build fewer cells. And certainly, you have to make sure that the battery is very safe. So to kind of set the stage for the challenge, I want to mention that there have been only 4 commercially successful rechargeable battery chemistries in history. Of course, there is the lead-acid batteries, which are currently still utilized. And then there was the development of nickel-cadmium batteries, then nickel-metal hydride, and eventually intercalation-type lithium-ion, the inventors for which received Nobel Prize in Chemistry in 2019. And so each of these material innovation enabled battery to gain higher specific energy, so battery became lighter, and they also enable higher energy density, so the batteries could pack more energy per unit volume. And now I think the time is very exciting because we see the emergence of the 5th type of batteries, conversion-type lithium-ion, which will enable further improvement in performance and at the same time, significant reduction in cost. For those of you who are less familiar with lithium-ion battery operations, I have this simple schematic. So you have 2 electrodes, cathode and anode. Cathode is typically comprises lithium because lithium is happier in the cathode, and it's easier and cheaper to assemble battery in the discharge state when the lithium is already in the cathode. And so once you assemble the battery, you charge it at the factory, so you move lithium from the cathode to the anode. And so when you allow the battery to do some useful work, let's say power your laptop or your cell phone, then the lithium comes back to the cathode. And so the difference in electrochemical potential between the anode and cathode defines the cell voltage, the lithium-ion battery voltage. And the capacity of the electrodes, or how much lithium each electrode can store, defines capacity of the battery. And how fast you can move the lithium back and forth defines the power performance or charging speed. Conventional lithium-ion batteries utilize intercalation compound. What it means? So you have these crystal structures that store lithium-ion in the interstitial positions. So this is an example of lithium cobalt oxide, the one that you use in batteries to power your cell phone or laptops. So when you move lithium back and forth between anode and cathode, you reversibly insert lithium back into the structure, or they call it intercalate lithium back into the crystal structure. And the process can be very reversible because there are very little changes in crystal structure, no changes in chemical bonding, and overall very nice system. However, it requires these multiple host atoms for lithium. And so it affects the weight of the battery, and it certainly affects the cost if you have to use expensive elements, such as cobalt. And then there is a new type, conversion type lithium-ion batteries, which people are exploring, that have much higher capacity. You need much fewer atoms to store a lot of lithium. Many of these conversion type materials can be built with abundant elements. The challenge is that during lithium insertion, you always break chemical bonds. In addition, you have dramatic volume changes. And furthermore, many of the conversion type electrode materials, especially the cathode, they tend to dissolve during cycling. However, if you look at the changes in the lithium-ion battery market for the last 30 years since the invention of the first commercialization of lithium-ion batteries, you will see that initially for the first few decades, the price and performance has been steadily changing, right? Price have been reduced quite dramatically, and the performance was also steadily increasing. But in the last decade, even though you hear about all the breakthroughs in the literature, you will see that the price kind of stabilized in the sense that the changes in pricing have become smaller and smaller, and improvement in performance have also stagnated. So what do we do now? One way is to go to this new type of chemistries for lithium-ion, conversion type lithium-ion, that will enable better performance, hopefully within the next decade, and significant cost reduction. There are additional issues with conventional lithium-ion battery chemistries. So for example, all the high-performance cathode materials used in electric vehicles, they comprise nickel and cobalt. And supply of these materials in Earth crust is very limited, especially if you consider commercially viable supplies. And so because of this significant increase in demand for the lithium-ion batteries, we expect that within a decade, we will face a shortage of cobalt and shortage of nickel. And so as a result, the prices for cobalt and nickel might go up, and that is exactly not what we want to have, right? We want the price for lithium-ion batteries to go down over time, not up. And so you can also notice that in the last few years, already the prices for cobalt and nickel are skyrocketed. They increased by 2x. Furthermore, another point I want to mention is that distribution of these metals in Earth crust is very non-uniform. Majority of supply of cobalt, for example, is in this Democratic Republic of Congo. In US and Europe, there is no cobalt and very little nickel. So you also have a lot of nickel. You have much more nickel than cobalt in automotive high-performance batteries. And supply of nickel is much larger, but you need more of it. And so again, we expect significant shortages of nickel, and so within a decade or so, the price might start going up. And so the current price is about $20 per kilogram, but again, it's almost twice as much as in 2019, a few years ago. Now, in addition to that, there is significant price pressure to reduce the cost of the raw materials, raw minerals. And so many mines in developing countries compromise on safety of workers, compromise on protective equipment, and sometimes cause major pollution. Nowadays, more and more automotive companies become very thoughtful about their supply chain, and they want to make sure that whatever cobalt or nickel they use in their automotive batteries, they come from kind of clean mining companies, that companies that mine these minerals ethically, right, without contaminating the environment, without making people sick in the process. But this is still an issue. And so I mentioned that the cost and performance of this new chemistry can be quite lower. Performance can be higher, and the cost can be lower. How can I say that? Well, if you look at lithium-ion batteries, and depending on the configuration, it can be cylindrical, can be prismatic, can be pouch type, but if you open it up, you will see it consists of the same building blocks, right? You have current collector, aluminum for the cathode, copper for the anode. You have electrodes, so anodes and cathodes with active material and some porosity, because everything is immersed into electrolyte, and so lithium-ion propagate through electrolyte. And then there is a separator that electrically separate anode from cathode. And so you can have certain assumptions on the properties of these separate foils and electrodes, and you can estimate, depending on what composition of the cathode and anode, what kind of energy density or specific energy or volumetric energy density you can get. And you can estimate that if you move this transition to purely conversion-type chemistries, you can expect up to 2 times improvement in volumetric energy density and up to 3 times improvement in gravimetric energy density. And so both volume and mass matter, because as I mentioned, the higher volumetric energy density gives you longer driving range in cars, right? And also lower cost. And lighter weight is important for, let's say, electric trucking, right? Because the batteries, current batteries are too expensive for many applications, right? Not expensive, well, expensive too, but they're too heavy for many applications. It reduces the payload of trucks, and so going to lighter batteries will overcome this challenge. In addition, for anything, if you think about, let's say, flying cars, if you think about drones, if you think about electric aviation, they need lighter batteries. In fact, if you look at the cost structure of the flight, more than 50% is the cost of the fuel. Even though the planes are not cheap, but majority of the cost is the cost of the fuel. And so electricity is dramatically cheaper, and the only thing that stops planes from using batteries is their weight. So if you reduce the weight by 2-3 times, right, you may enable electric aviation, which will be good because of the reduced cost, but also will be certainly great for environment. In addition of these potential advantages, many elements that are used in conversion-type cathodes, such as sulfur, copper, iron, are available in massive volumes, and they're very low cost, especially iron and sulfur, and on the anode side is the silicon. And so we could do some predictions how much the price for the lithium-ion batteries you may expect with certain performance improvements and certain maybe evolutionary reduction in the cost of manufacturing. And if you look at the cost of actual cost in 2019, you will see that this data are given for different battery chemistries produced in different countries and different cell form factors. So it's not apple-to-apple comparison. However, you see certain trends. And you will see that batteries, for example, that have higher energy density, so higher, more watt-hour per liter, are actually cheaper. So they have higher performance, but they are less expensive by normalized by kilowatt-hour. And why is that? Well, because the manufacturing becomes cheaper, you need to make fewer batteries, right? In addition, you have a less inactive material. Because you need to build fewer batteries, you need less separator, you need less electrolyte, you need less foils, and so forth. So you have this cost savings. And so you can predict when the transition from the intercalation-type graphite to silicon happens, what kind of performance improvement you can get, and what kind of cost reduction you can expect as a result. And our assumptions in this paper have been very conservative, and still we expect that with silicon anodes matched with high performance intercalation-type graphite, nickel-based cathodes, all the cost of the batteries will be below $75 per kilowatt hour. And again, as I mentioned, it's likely conservative. And if you look further along, when you have conversion-type cathode materials, then the price is going to be reduced to well below $40 per kilowatt hour. However, if you have to stay with intercalation-type cathodes, the price is going to be much higher, especially if the prices for nickel and cobalt keep rising. And why it is so exciting is because you see that the transition to electric transportation is inevitable. Essentially, at this price point, the cost to build Model S, high-performance vehicle, right, will be as low as that of the modern-day Camry, but it will provide you much more fun to drive, right? It will provide you with cheaper fuel, right? Electricity is much less expensive compared to gasoline. In addition, you will preserve environment and prevent further climate change. So super exciting. The question is how fast we can get there. And as I mentioned, the development of high-performance silicon anode is the most critical milestone. So it has about 10 times higher gravimetric capacity compared to intercalation-type graphite. It has about 3 times higher volumetric capacity at the cell level for the same cathode and the same separator, foils, and so forth. It provides over 40% energy boost. It is also widely, globally available. It is as much silicon in earth crust as all other metals and semi-metals combined. Right? It comes from sand. The only problem is that it is challenging to use. It is challenging to stabilize. So I want to highlight a few challenges. So when you insert lithium into intercalation compound, as I mentioned, there are very little volume changes. So there are very moderate stresses that occur. Silicon takes so much lithium that it changes in volume. And all these changes, if you have gradient in lithium concentration across the particles, it may build up internal stresses. And if the stresses exceed the value related to fracture toughness of the material, you may have pulverization, right? So large particles will pulverize into smaller particles, and the batteries may degrade. Another challenge is that when you lithiate silicon, it expands so much, right? And when you have a lithium-ion batteries, the anode is at such a low electrochemical potential that all electrolytes that are currently being used become electrochemically reduced, they decompose. So when the volume changes in the material are small, this decomposition product may form a very stable solid electrolyte interface, or ACR layer, that prevents further electrolyte decomposition. However, if you have such dramatic volume changes, it's very difficult to stabilize the ACI. So you have this electrochemical degradation of batteries induced by volume changes. And certainly, if your particles swell so much, you don't want your battery to swell, right? You don't want your cell phone to swell, right? This has to be dealt with as well. And so when I joined Georgia Tech over a decade ago, I started to look into fundamentals of silicon chemistry. And together with other colleagues around the globe, we realized that small particles can be made stable, right? You will have no mechanical instability in small or nanoparticles of silicon. However, small particles always have very high surface area, so all this electrolyte decomposition now happens at much higher surface area, so you have much larger degree of undesirable reactions, right? So you can have even faster degradation. Then we also realized that if you form composite materials, you can overcome volume changes at the composite particle level. And finally, we realized that if you have this core shell morphology of the particles, when you have a shell and you have porosity within silicon that can accommodate this well, and the outer dimensions of the particles may not change, if you have a constant outer dimensions of the particles, then in this case, ACI, or this solid electrolyte interface, can be made very stable. And so with this in mind, we started the company. I founded 2 amazing co-founders, with entrepreneurial expertise in hardware technologies. And we started in the Ford building in technology incubator space and gradually grew the team from a few people to now about 300 people, very interdisciplinary team of scientists, engineers, staff, all working together to commercialize silicon and other technologies related to the future of lithium-ion batteries. We currently occupy 3 buildings in Alameda, California, so we moved the company to Silicon Valley like 5 years ago. And so, also trying to secure now a much larger building, much larger facility to build a gigafactory, a factory producing enough material to power up to 1 million electric vehicles per year. We were fortunate to receive significant support and trust of our investors and increase the company value. So when we started the company, we envisioned that we wanted to develop a certain type of product. We wanted to make sure that our product will be compatible with lithium-ion battery factories, present, past, and the future. And so conventional materials, they're typically micron scale. So we want to develop micron scale particles that would also exhibit very small volume changes at the particle level in order to get this stable ACI. And we also wanted to make sure that whatever we develop is going to be manufacturable economically at a global scale. What it means that when you build large reactors, the large reactors should be inexpensive to build. It means that if you use some materials or precursors, they have to be inexpensive and available on massive scale. So it put significant restrictions on us, but it was worth it. In addition, it's always easier said than done. We faced multiple technical challenges. So when you have, let's say, electronic device, a transistor, so atoms in the transistor, silicon atoms, stay put, right? Only electrons move, right? And electrons can move back and forth in the transistor for billions of times without damages. However, if you have a lithium-ion batteries, you have the host electrodes, host atoms, they stay put, but lithium moves back and forth, right? And this is traditional intercalation-type lithium-ion. So when you want to move to conversion-type lithium-ion, then every single atom moves during charge and discharge. And you have to make sure this motion is fully reversible. Because if any single atom loses its way to a side reaction, 1 out of 10,000 atoms loses its way in a side reaction in a single charge-discharge cycle, then your battery will not last as long as it should. So we have to take different steps from very different industry to realize it, vision, to make sure this motion of atoms is fully reversible. In addition, we early realized that small experimental variations may hide the signal. So when you develop something, right, you want to change one parameter and you see how it affects, right? And if you have very small signal, right, then if you have not very precise equipment, you're in trouble. And particularly if you have process that takes multiple steps, right? You have error in each step, then you see noise in the output, even if you change some parameters. So we had to develop high-precision reactors and make sure we can control the process at a remarkable rate, much higher than we could do at an academic lab. We also learned that when you develop new materials, in many cases, there are no characterization techniques available to characterize them. So we had to develop our own unique metrology tools, our own unique characterization tools. We certainly relied on the commercially available tools as well, but we had to develop our own, including our own software. I also want to mention that in many academic literature, key performance requirements are often overlooked. And as I want to highlight some of those, and many of this, even I was not familiar with when I developed technology at Georgia Tech at the early stages. So we had to overcome it at the company. So first of all, as I mentioned, swelling is very important, and we have to make sure we can control it. So every electrode, even intercalation materials, they change volume in each cycle, charge, discharge. They expand and contract a little bit. And when we develop our materials, we wanted to make sure that we have control over these volume changes. And so the unit stack thickness change is very moderate, very small. Otherwise, it will be very challenging to get high performance in large automotive cells. And so Unisil could achieve that some time ago. In addition, there should be no long-term swell, right? Because if the battery swells gradually, right, eventually you'll come to a problem when, I don't know, if you have an electronic device, maybe your screen can pop off, right? If you have in a car batteries, it's going to be a disaster, right? Because if the car battery breaks, it has so much energy, it can go on fire. Your whole house can go on fire. That's very problematic. You have to make sure there will be no long-term swell. In addition, when the materials are processed in lithium-ion battery facilities, the current requirements is to reduce CO2, reduce emission, reduce the use of harmful chemicals. And so you have to make sure your technology, your particles in our case, would be compatible with the best technology on the market, in this case, water-based electrode processing. And so Sila had to overcome it. And in fact, the performance of high-performance batteries with silicon anodes are actually better than high-performance batteries with otherwise analogous, but with graphite anodes. Smaller swell, better performance. In addition, when you have a safety test for the batteries, typically what you do, you charge the battery to high voltage, and you hold it at high temperature for quite some time, and then you see if the battery swells or it doesn't, right? How much capacity it retains. And this test is actually cell-specific, so you have to build the proper cell in order to test it properly. And certainly in academic environment, we cannot build high-performance large batteries. In addition, if you have this high voltage, high temperature hold, it has to retain not only capacity, but also has to retain high voltage. If the impedance rises, if the voltage becomes smaller, it's a huge problem. And certainly there should be no end-of-life gassing. So when the battery dies, you don't want it to explode. And this becomes very critical, particularly for automotive cells, right, that have to last for decades. In addition, there should be low self-discharge, right? And so, again, typically you heat the battery to certain temperatures and look at the leakage current. And again, you have to make sure that materials you develop, in our case, silicon anodes, would have a lower or at least the same leakage current compared to the high-performance graphite anodes. The calendar life, as I mentioned, is very, very important, particularly for automotive applications, right? In consumer cells, the cell phones, people typically change them every few years, right? So the calendar life is less important. But if you buy a car, electric vehicles, right, and you pay significant price for it, you want it to last at least a decade, preferably a few decades, most preferably 3 decades or more. And another important parameter is that high performance and high rate performance in fast charging at different temperatures, both high temperatures, room temperatures, and also cold temperatures. And these are a lot of requirements that are not easy to overcome. And so when you report some new scientific discovery in academic literature, you probably don't test it all. In many cases, what we notice is that many, let's say, solutions that people thought are promising are completely unusable in industry because of some of these limitations. And so with significant resources, and again, took us much longer time than we expected, but the company did develop high-performance anodes, drop-in replacement anode materials that would offer very good performance at high area loading. So area loading is how thick your electrode is. And so it is important to produce the loading that will be compatible with industry standards. The higher the better, because you will use less amount of inactive materials in the cells. And so high performance characteristics, high loading, low first cycle losses, and high capacity. So our materials offer about 5 to 6 times higher gravimetric capacity compared to graphite. And because it's composites, it's not pure silicon, it's not as high, but in terms of the volumetric capacity improvement, it's almost comparable to pure silicon. And this is an example of automotive cell, and again, over 1,000 cycles. So if you have a vehicle that would have, let's say, 300-mile range, 1,000 cycles means it can drive for 300,000 miles. Again, typically sufficient for many applications. If you have autonomous vehicles, the demand will be higher. So you probably would need, let's say, something like 3,000 cycles to satisfy this demand, to have, let's say, a 1,000,000-mile battery. And it is all feasible. In automotive cells, the loading is typically higher. And again, another important parameter is that you have this energy density gain, right? You have higher performance, but you don't want it to you want to make sure it's not at the expense of something else. It's not at the expense of safety. It is not at the expense of fast charging. And so, in fact, with silicon, because the anodes are thinner compared to graphite, and the charging time is related to diffusion through this electrode thickness, diffusion of lithium ions. The thinner the anode, the faster you can charge, right? And so we can enable this fast charging almost effectively for free. In conventional batteries, if you want to develop fast charging, you have to sacrifice something. So typically, people sacrifice energy density and the cost. If you want to have high fast charging, the batteries become cheaper, right? And the vehicles will be able to drive to shorter distances. In addition, so we assemble our particles from ground up, so from liquid and gaseous precursors. And so we can make them of any shape. We can make them spherical shape. And spherical shape is attractive because it enables you to have very low tortuosity within the electrodes, right? And so again, it's very good in terms of fast charge and discharge. In this case, we cycled the cells quite some time ago, and showed that individual particles are very fast. You can charge individual particles at extremely fast rates. And then if you design electrodes properly, then you can also have very low tortuosity and fast charging available. And so the first product that the company developed is this silicon-based composite powder that increases energy density of cells to about 20 to 40%. It works today. It is fully compatible with all factories, and you can build cells of any form factor, from small coin cells in electronic devices to very large automotive cells. And there are many advantages to everybody. So for example, if you have a gigafactory and it supplies, let's say, 1 million electric vehicles, you use our technology, and now the same factory can supply cells to like 1.2 million electric vehicles, right, or more. And so you have larger production without any investment in the capex or overhead. You also have reduced depreciation per energy, normalized by energy, and again, very important, reduced CO2 emission, right? You have to build fewer cells per watt hour, so you have a reduced CO2 emission per watt hour. We were fortunate to build a very strong partnership with automotive companies. Those two have been publicly announced. So both Mercedes-Benz and BMW are going to build these amazing cars with the best batteries in the world using similar technologies. And they're going to be absolutely amazing. I'm going to get one of those myself. And so once you solve the anode problem, you have to move forward. And so the next challenge is the cathode. How do you develop high-performance cathodes? And it is equally challenging. It's probably even more challenging. So cathodes, as I mentioned, they're also conversion-type cathode materials. They change volume, maybe not as much as the silicon, but still there are significant volume changes. But the biggest issues with the cathode is that the cathode is much more reactive. The conversion-type cathode much more reactive with electrolyte. It induces gassing, and also, unfortunately, all conversion cathodes, to some degree, they dissolve during cycling. At some point of charge or discharge, they produce soluble species that dissolve. And that's a huge problem, right? You dissolve your active material, you also have precipitate on your anode, right? And the resistance of the cells keep increasing. That's a huge problem. And so there are multiple solutions to that. And so there are multiple ways you can solve it at the cell level. You can do optimization of electrolytes. You can also design particles. And particles, I think, is the most attractive approach because everything else can be kept the same and kind of drop in replacement, as I mentioned. And so, as I mentioned, there are two candidates for conversion-type cathode materials that probably have the future. One is sulfur-based, lithium sulfide, and another one is metal fluoride-based. So you can use the sulfur-based cathode in a lithium-free state, right, as a sulfur, very cheap material, or you can use it in a fully lithiated state as lithium sulfide, Li2S. And I think, again, I'm going to share my personal opinions. Lithium sulfide is likely going to be material of choice for several factors. First of all, it's already in a fully expanded state. It's much easier to deal with particles in a fully expanded state. It can also be compatible with lithium-free anodes, and lithium-containing anodes typically much more dangerous to use in factories. In addition, I think all these materials would have to be nanostructured, similar the way that silicon is nanostructured. They have to be protected from side reactions using shells. And the synthesis, again, have to be inexpensive, has to be very precise, and there should be no excessive pores of inactive materials in these composite particles. And now there is significant research, Tesla announced it, right, dry processing of electrodes. And I would say lithium sulfide would be particularly Advantageous to use with dry processing because it's more reactive. It's sensitive to moisture. So if you have dry processing, it's probably going to be advantageous even more for this particular technology. And so if you make, let's say, these particles, lithium sulfide particles, as I mentioned, during some point of charge and discharge, they tend to form polysulfides, long chain polysulfides that dissolve into electrolyte. So how you overcome this challenge? If you use lithium sulfide, it has very high melting point, very good thermal stability. You can heat it up to, let's say, 800 C. And then if you have the thermal stability, then you can deposit all sort of coatings on the surface of the particles that would prevent direct contact between electrolyte and active material. And so that's what we did some time ago. And so again, if you have this nanostructured material with core shell protection, you can get some decent stability to some degree. Unfortunately, the coating is not very stable. During charge and discharge, the particles change volume, and typically the coating fails at some point. Then you have a start dissolution. And the problem becomes particularly important for high loadings when you have thicker electrodes. You have more dissolution products, you have resistance raising, and so forth. And then you have to use some special electrolyte to try to minimize the damages. Some of the electrolytes have this kind of self-repair mode. Once you have this breakage in the shell, you can kind of repair it. You can try to repair it. It's not very effective, though, but helps. And so another way to overcome it is to design these hierarchical particles when you have multiple levels of protection and when you have nanoparticles immersed in some sort of matrix material. In this case, the overall volume changes are smaller, right? So you can prevent cracking of the shell during charge or discharge. And you can also minimize probability of this polysulfide formation and leakage into electrolyte. And so there are multiple ways to do it, but we developed very simple methodology, some time ago. So effectively, we found that lithium sulfide can be dissolved in ethanol and methanol, some organic solvents, to a decent degree. And if you have let's say, a polymer that can also be dissolved in the same solvent, and if you simply dry the solution, at some point, lithium sulfide will start precipitating, right, as nanoparticles homogeneously. And then, because if you use a polymer which has polarity on the surface, and lithium sulfide is polar, you're going to get coatings of the polymer on the surface of lithium sulfide, right? It may prevent ripening of the lithium sulfide particles, crystallization to larger sizes, which we want to avoid. And so then at some point you will form these clusters of lithium sulfide nanoparticles within this polymer matrix. And because lithium sulfide is thermally stable, you can carbonize it, right? And you can produce lithium sulfide nanoparticles embedded in these carbon composites, elastic carbon composites, which you can further protect with the shell. And so when you do this process, you can demonstrate that you can produce pure lithium sulfide and carbon composites without anything else, without any side products. And if you do microscopy, you can demonstrate that, yes, you produce what you plan to produce. In this case, we demonstrate these relatively small particles, sub 100 nanometers dimensions, but they compose even smaller particles of lithium sulfide embedded in this carbon matrix and further protected with this outer graphitic shell. And so typically when you charge discharge batteries at high temperatures, it tends to degrade faster. But here we demonstrated, again, you can retain very high stability, very high capacity too, in elevated temperatures, 35, 45 C. And the difference between charge and discharge is called hysteresis, is very small. It means that the energy losses, even though you use conversion process, conversion material, sometimes people believe that if you have conversion process, if you have to break, restore chemical bonds, you will lose a lot of energy. And this is, you do lose more energy, but it is still very small compared to everything else. So you can have a small hysteresis, you can have good energy efficiency in this process. You also don't have to use, certainly, carbon. You can use a variety of other materials as a shell. And what we found that many oxides, they have very interesting properties. So we found that some of the shells that we try to produce, they were not formally conformal. They have holes, and yet they help to retain stability of these materials, which was very puzzling for us. And later we realized, in collaboration with Oleg Borodin from Army Research Lab that had done some modeling, we realized that these long-chain polysulfides, they decompose on the surface of many oxides and form in much shorter chain polysulfides that have dramatically lower solubility in the same electrolytes. So you simply dramatically reduce solubility of the byproducts that you potentially form. So maybe a good idea would be to combine some of these ideas together. And so you can achieve a good performance and certainly, certainly better performance if you have these oxide coatings that would induce decomposition of long-chain polysulfides for many cycles, for hundreds of cycles. Now, the next material which I want to mention for the conversion chemistry is metal fluorides. It's a true conversion, so essentially if you start with metal fluoride and you lithiate it, you produce a nanocomposite. You produce, in this case, lithium fluoride and iron nanocomposite. And if you look at this reaction and you want to make sure it is fully reversible, you realize it's probably very hard. How can you make it fully reversible? Lithium fluoride has also very high resistance. It's a very good dielectric material, has high band gap, so it's very resistive. In addition, one of the biggest challenges we found was that the interface between lithium fluoride and metal is high energy. So lithium fluoride doesn't like to be near the metal, or the metal doesn't like to be surrounded by lithium fluoride. And so they tend to overall ripen or increase in dimensions over time, and you have even larger mass transport limitation. And furthermore, both metals and lithium fluoride can dissolve into electrolyte at high voltages. And furthermore, you also have, these metal nanoparticles that you produce, they often serve as good catalysts. And so they decompose the electrolyte and have all sort of side reactions that, again, are important to avoid. And again, if you look at the more broadly, you probably need to use lithiated version of the material to be used in lithium-ion batteries. And again, you have to nanostructure it. You have to protect it with shells. You have to nanoconfine the particles. And probably you're going to use iron as a metal. And metal fluorides, because iron is very cheap, very inexpensive, and you can have very high capacity, both gravimetric and volumetric capacity of these materials. And in addition, there are a huge amount of waste products of metallurgical industry. And so this iron that is already treated with HF, that has fluorine, is available at essentially negative cost. You have to pay to get rid of it. And so if you can use it as an input material for your metal fluoride particles, that would be outstanding. You can have very low cost production. And then one of the challenges that, as I mentioned, is the segregation of the particles, and the high resistance of the lithium fluoride could be overcome if you simply nanoconfine it. And in this simple example, we nanoconfined these metal fluoride particles within activated carbon. In a very simple process, infiltrate precursor, convert it to metal fluoride. And so then you don't rely on metal to conduct electrons. You have this carbon matrix to conduct electrons, and you use this nanoconfinement in order to prevent ripening, separation, phase separation between metal and lithium fluoride during cycling. And then, we demonstrated, quite some time ago, you can achieve hundreds of stable cycles at this high capacity. You can also use different procedures. You can start with the precursors that would comprise both precursor for the carbon scaffold or matrix material and precursor for the metal fluoride. So in this case, we use nanofibers. We use electrospinning technique. You can use different techniques to produce spherical shaped particles or particles of whatever shape you want. And again, you can have very high uniformity in these composites, and depending on optimization conditions, again, you can have high capacity and very stable performance for many, many cycles. So, unfortunately, metal fluorides are very tricky. Even if you figure out how to make them stable at room temperature, if you want to go to much higher temperatures, as I mentioned, batteries have to operate at elevated temperatures. You have to expose them to 70, 80 degrees C, right? And in these conditions, if you have metals that catalyze some side reactions, it becomes problematic. So those cells that have decent performance at room temperature, even at 50 C, typically they plummeted in performance. They decrease in capacity very rapidly in liquid electrolytes. And so there are two challenges, two ways to overcome it. Either you figure out how to make perfect protective coating, so these materials didn't have any protective coatings, or you can use electrolytes that do not react, do not have these significant reactions with active material, right? That do not dissolve these materials. And so then, in this case, we use polymer electrolytes, and you could achieve, good stability. Another advantage might be a synergy between polymer electrolytes, or many solid electrolytes, and conversion-type cathode is that many solid electrolytes that operate well at low electrochemical potentials, they have stability issues at high voltages. And these conversion-type chemistries, they don't go to high voltages. They have very high capacity, but the voltage is smaller. But in that sense, it's much more compatible with polymer electrolytes or with other types of solid electrolytes. Now, you can go all the way to ceramic electrolytes as well. There have been lots of studies and lots of excitement about ceramic solid-state electrolytes. And there are pluses and minuses. And it's still unclear if this technology is ever going to be useful because ceramic electrolytes are much heavier and they're much more difficult to process, right? So you have to, if you want to make all ceramic batteries, you have to have all ceramic electrodes. You have to sinter them at high temperatures, which is expensive, right? You have to use very different processes, completely incompatible, or partially at least incompatible with all production of lithium-ion batteries worldwide. And people already build in factories. They committed tens of billions of dollars, if not hundreds of billions of dollars, to build all these gigafactories around the globe, right? And if technology is not compatible with these factories, it's a huge problem for deployment. And so we thought, okay, it would be nice if we can use maybe solid electrolytes to prevent some side reactions, maybe that would offer better safety, but that would be fully compatible with conventional lithium-ion battery production, right? If you have, let's say, solid ceramic sheets, right, to try to sinter it is much more difficult. But what if you have electrolyte that may be liquid at moderate temperatures, maybe at 100 to 300 C it's liquid because it has a low melting point, but it is a solid at room temperature or at operational temperatures. And so we found quite a few interesting electrolytes that can do that. And another interesting feature is that these electrolytes that have very low melting point, fortunately, or maybe not fortunately, but actually it makes sense, they're also lightweight. They have low density. So you have a density which is even lower compared to density of liquid material and a dramatically lower compared density of some of the solid electrolytes people are considering, like garnet electrolytes. And so when you have these molten electrolytes, another interesting feature that you can have wonderful contact between the electrolyte and active particles. So if you have a good wetting behavior, you can wet your electrodes really well, and you can have very low charge transfer resistance. So in this study, we used different types of materials. We used both intercalation materials, such as NCM or nickel, cobalt, lithium, nickel, cobalt, manganese oxide. Again, it's very common material for use in electric vehicle applications. We use graphite, we use LCO, but we also use conversion-type lithium sulfide cathode. And so because of the low melting point, right, there is no side reactions, right? If you don't have to heat the material at very high temperatures, your active material and your electrolyte won't react with each other, which is super nice. And we have multiple confirmation of that. So we built these full cells, and the performance was eventually quite good. We can have high capacity, we have small hysteresis, we have good overall characteristics, but we also noticed that the cell degradation does take place. And the challenge comes from the fact that, as I mentioned, all materials, even intercalation-type cathodes, they have some volume changes during cycling, right? You extract lithium from NCM, actually it swells a little bit, and it contracts a little bit. Liquid electrolytes are very good in accommodating these volume changes. But if you have solid ceramic electrolyte, the accommodation is much, much harder. And so to overcome it, you have to figure out either how to design cathode particles that would have, again, even smaller volume changes, preferably below 1% volume changes at the particle level, or figure out how to deal with the interfaces, making sure it can accommodate some of the swelling at the interface between active material and electrolyte. And so even though lithium sulfide, in principle, has much higher volume changes, but if you assemble it in a fully expanded state, it doesn't have to expand anymore. And in fact, we could achieve very good cycle stability for the lithium sulfide and the same technology, melt-infiltrated electrolyte technology. And finally, I want to briefly mention, maybe in the last 2 minutes or 3 minutes, another technology which we developed at Georgia Tech, which I think is very promising. So conventional electrolyte cells, as I mentioned, have a polymer separator that separates anode and cathode. And polymers are wonderful material. It's easy to process. The problem is that they typically have not very good thermal stability and not very good mechanical performance, especially at elevated temperatures. And if you miscalculated something, right, if you have some additional pressure within your stack, and if you overheat your cell, the separator can fail. Then you have a short circuit between anode and cathode, and then you can have a thermal runaway event. You can have it in cell phones, and God forbid, you may have it in an electric car. It's a huge problem. Can ceramic do a better job? It certainly can. And why nanowires would be good? Because ceramic is a brittle material. Bulk ceramic is brittle, right? However, if you have nanofiber formation or nanowire formation, brittle materials become very flexible. And so if you can build ceramic nanofibers, you can overcome these challenges. In addition, if you build fibers, then the smaller they become, the stronger they become as well. So you have high flexibility for small fibers, and they also become much stronger. And so there are multiple conventional ways to produce the nanofibers, but unfortunately, they all are very expensive. And so they're prohibitively expensive for electric vehicle applications, for battery applications, particularly for electric vehicles. And so we discovered a fundamentally new synthesis mechanism based on minimization of the boundary of the chemical, of the strain energy at the boundary of the phase transformation that allows us to transform bulk powders into nanowires. To simplify it, essentially, you can put your powders in a bucket, put some solvent, and then form a nanowires in a few hours, a few days. As simple as that. And so we demonstrated this process again some time ago. We published a paper in 2017. And so this is one simple example. So when you have a bimetallic alloy between aluminum and lithium, so if you put aluminum into alcohol, it's not reactive. But if you put lithium into alcohol, it forms lithium alkoxide that dissolves instantly. And so if you make these alloys between lithium and aluminum, if you put it into alcohol, then lithium dissolves. But when lithium dissolves, the aluminum becomes much more reactive, and it forms aluminum alkoxides. And what is fascinating is that it forms this aluminum alkoxide in the form of these nanowires. And you can convert, if you wait long enough, you can convert this alloy particle into nanowires, and they become dispersed in the suspension or suspended in the ethanol. And once you have the process, then you can choose different alcohols, right, different alloys as well, and you can tune the diameter of the nanowires. And you can, by defining the size of the initial particles, you can also define the dimensions of the nanofibers. And so you can produce pretty long fibers with tunable dimensions. And if you have these alkoxides, you can also very easily convert it to a variety of other materials, such as oxides, simply by heating them up. You know, they have a very nice conversion. And so once you have these, oxides, nanofibers, you can make ceramic paper out of them, right? You simply replace cellulose fibers with the ceramic fibers, and you produce the ceramic paper that have very good properties. It has a very good wetting behavior. It has a very high dipole on the surface, so electrolyte wets really well, and so you can have very fast charging in batteries. It also has remarkable thermal properties. You can heat it to 800 C, is not going to shrink because it's ceramic. So again, very good behavior for battery applications. And so if you cycle batteries, you will see smaller hysteresis, you will see better behavior, high rate performance of the separators. You can also incorporate them into polymers, make polymer ceramic composites that will also have maybe not as good thermal properties, but pretty good thermal properties. And you can also make ceramic nanofibers out of a variety of other materials using the same technique. We demonstrated magnesium oxide, zinc oxide, copper oxide, and other materials. So to summarize, I think the intercalation-type lithium-ion batteries are reaching their performance limits. And if you move to conversion chemistries, for example, silicon coupled with lithium sulfide or metal fluorides, you can overcome these limitations. You can enhance performance further and reduce costs. Silicon anodes are proved to be commercially viable and scale up as in process. Solid-state technology, in my personal opinion, has to be compatible with lithium-ion battery manufacturing to have a decent chance competing with liquid electrolytes. And I think ceramic electrolytes, ceramic separators built with nanofibers are very attractive. They can enhance safety, can improve performance, and without any cost, without changes in the cost structure. And with this, I would like to thank you, everybody who contributed to the studies. I have plenty of postdocs. I have also amazing collaborators from both national labs and also here from Georgia Tech, Tin Zhu, Alexander Alexeyev from Mechanical Engineering Department. We have been collaborating for many years. And with this, I would also want to invite those of you who are working in materials-related field to submit articles to Materials Today. It has a pretty high impact factor, so we're trying to catch up with Nature and Science. But please do submit your best work to our journal. It's also, we have a huge family of journals. So Materials Today is a flagship journal, but we have plenty of other journals in the family. And the impact factor of each of those is keep rising quite rapidly. And with this, I would like to thank our sponsors. I would like to thank David and Amy for inviting me to give this talk. And I'm open for questions. And I have to disclose the conflict of interest because the patents technology, Georgia Tech technology has been licensed to Sila. So both myself and Georgia Tech are stakeholders of the company. Thank you.
We do have time for maybe one or two questions.
Hi, thank you for your talk. I'm wondering, as an editor, a person in industry and in academia, how do you feel about you touched on the balance of like what gets reported in academic journals. How do you feel about the structure of papers and if they're being prohibitive towards presenting the whole picture at different temperatures and different like sizes of cathodes and things like that when it comes to moving the field forward? What are your thoughts on the structure of papers and that?
I guess there are two challenges. Of course, people want to report everything. The problem is that first of all, you have a pressure to publish a lot. To publish a lot, you don't have enough time to get all the tests done, and there is a pressure from academic environment, right? You're expected to publish so many papers to get tenure, right? To get promotion and so forth. In addition, there is a pressure from funding agencies. They expect 3 papers or 2 papers per year for the grant that funds a single student, right? It's very challenging to get it done. Furthermore, the size of the funding is typically insufficient to get all these tests done. Many equipment is very expensive, and many tests are simply, you have to have multiple people, right, reporting, and so it becomes very challenging in academic literature to accomplish something like this. And I honestly don't have a clear solution to overcome this challenge. And maybe academic world is better to report on some revolutionary discoveries that may or may not be used in industry, and the industry has to judge what makes or makes no sense to utilize.
Thank you. Hi, Gleb. Thank you very much. I was wondering if you could just comment a little bit on the challenges for binders for silicon anodes. For example, will PVDF continue to be used for silicon, et cetera?
Yeah, so PVDF in the past been used for graphite, but it is not used anymore. So almost like 95–99% of graphite anodes are using now aqueous binders, such as carboxymethyl cellulose and others. And I think silicon anodes would have to use the same. So you have to use water-based binder solutions, and CMC, and others work quite well for silicon. And again, silicon, it depends, right? So if you design particles that look like graphite and behave like graphite, you can use the same binders, right?
All right, I think in lieu of the hour, we're going to close here. I just wanted to thank Gleb one more time and wish you all a happy holidays and a happy new year.
Thank you so much. Thank you. Happy holidays to all.